Welcome to the run-through of the 2023 GCSE Physics Paper 2, and this is the higher tier that we're looking at today. First question, question about waves, infrared waves or transverse waves. You need to complete the sentence. So in a transverse wave, the direction of the oscillation is what compared to the direction of energy transfer. So the wave is transferring energy in that direction. The oscillations of the vibration are going to be up and down. So the best answer here is perpendicular. If you said at right angles, that would probably give you the mark as well. Now, question 1.2, straight into a 6-mark question already, but it's quite a nice one to look at. So we've got a student investigating how the colour of a surface affects the rate at which the surface emits infrared radiation. So we've got some equipment that could be used. We've got our kettle, got water in it, and we've got our silver flask, and we've got the black coloured flask. Now, obviously, if you're aiming for 5 to 6 marks, you need to come up with a method which would give valid results, and you need to sequence it properly. So the first thing to do would be, well, first of all, read the hypothesis that the student has written, that the black coloured flask will emit more infrared radiation than the silver coloured flask during 10 minutes of cooling. We've got to describe the method to test that hypothesis. Well, clearly the first thing we need to do, if we're talking about cooling, we need to heat the water. So we need to boil the kettle. So heat the water. Now you need to think about our variables, and we've got to make sure that we make this test as fair as possible. So we're just comparing the black coloured flask with the silver coloured flask. So we need to make sure that we add an equal volume of hot water to each flask. We need to place our thermometer into each flask. So with a thermometer, measure the starting temperature. Now, ideally, we need that starting temperature to be the same, because it makes it the fairest test possible. So we then need to leave our flasks for 10 minutes. And then at the end of that, we need to record the temperature again. So we record the change in temperature, and then all we need to do is compare the two sets of results in order to test the hypothesis. Now, to be fair, this isn't the most complicated method, but just make sure you got all those points down. Now, when we talked about leaving the flasks for 10 minutes, you could talk about using a stop clock or a stopwatch for timing, if you just want that bit of completeness. The other way you could do this is, rather than using necessarily a thermometer to record the temperature, you could use an infrared detector placed at equal distances from each of the two flasks. However, if you just go down the easiest route, or the easier route using a thermometer, that would get you the full 6 marks. Now, to get your level 3, which is your 5 or 6 marks, you've got to have a correct way of measuring the temperature decrease for both flasks, or whether you use the infrared detector. So hopefully you've got 6 marks, and it's quite a nice start to that particular paper. So on to question 1.3. So the question is, when will the flasks emit infrared radiation at the greatest rate? we've also got to give a reason for that answer. Now, this is one of those things that you just need to remember, is that the hotter something is, the greater the rate at which it emits infrared radiation or cools down. So, because we're starting off with very hot water, the answer is during the first minute, and that's because we have the biggest temperature gradient. There is the greatest difference in temperature between the water and the surroundings. So remember, you get the first mark for ticking the correct box, and then of course you've got to give the correct reason. If you didn't tick the correct box, it doesn't matter what reason you put, you don't get any marks. Right, and then another student investigated the absorption of infrared by different surface colours. So this time the student filled 4 hollow metal cubes with cold water. Each cube was the same size but had a different surface colour. The cubes were then placed the same distance from an infrared heater. After 10 minutes, the student measured the temperature increase of the water inside each cube. So question 1.4, what was the dependent variable in this investigation? So whenever you get anything like this, dependent variable, what did you measure? Well, in this case, it's a temperature increase, T increase of the water at the end of the 10 minutes. So again, variables come up all the time. Make sure that you remember them. Now, question 1.5, we've got our table of results. So we've got the surface colour of each of the cube, and then you've got the temperature increase after 10 minutes in degrees centigrade. We need to give 2 conclusions that can be made from the table. Now, from this, you can see quite clearly that in both cases, black surfaces absorb more infrared than white surfaces. So I'd go with that first of all. So black surfaces absorb more infrared than white surfaces. And then the other point I'd make is the fact that matte surfaces again are better absorbers than shiny surfaces. So matte are better absorbers than shiny. They're the best 2 answers to get both marks in this particular case. So use the information on the table. You're comparing black and white, shiny with matte. That's where your two marks come from your 2 conclusions. Right, and then we're into a bit of a maths question, but before that we need to work out our formula. Now, it's saying here we need to use the formula sheet, but as far as we're aware, you'll not have that formula sheet. So this is one of the equations that you need to know. So we've got one of the cubes, we've got the diagram there. The cube is filled with water. The weight of the water exerts pressure on the bottom of the cube. We just need to know the formula. Pressure is force divided by area. So there's only one possible answer there. And then of course we need to use that information in the next question. So if you remember, pressure equals force over surface area. This is worth 4 marks. Now that just seems unbelievably generous, but the first thing we need to do is we have to work out the surface area. So on that previous question, it said that we need to work out the area of the base. So the area of the base is 0.12 multiplied by 0.12 of a metre. Now that gives you an area of 0.0144 square metres. Now just by working out that area, the surface area, we've got our first mark. We're now substituting the numbers that we've got. So we've been given the pressure, we've got to calculate the force. So F is going to be the unknown, and we've just worked out the area. So substitute in the numbers, we end up with that 0.0144. We've now got a second mark. We need to make force the subject of this equation. So we have F equals, well, we need to multiply both sides by 0.0144 to get off the bottom. So we have 1500 multiplied by 0.0144, and that comes up with an answer of 21.6 newtons. Now, if you wrote 21.6 newtons in there, you'd get the mark. You could also round it up to 22. Either way, you would get that fourth mark. So remember, with our maths questions, just this, like I said, this is generous. So you get 1 mark for calculating the area, the second mark for substituting in the numbers to the formula, third mark for making force the subject, and then the last mark is to calculate the correct answer. Now that's a big long first question. It's worth 17 marks. Hopefully you got 17. Now question 2. We've got a figure 3 shows the route an aeroplane takes as it travels from an airport terminal to the runway. Figure 3 has been drawn to scale. Now the question they're asking is determine the magnitude of an aeroplane's displacement from the start prior to the finish point on figure 3. Now, because of the way this has been scanned in, and you could be looking on this on a different size screen, it's quite tricky. Now, just explain how to do it. All you need to do is you would put your ruler, and remember displacement is in a straight line. You need to measure that distance from start to finish. Now, on the actual exam paper, that is a line 7.1 centimeters long. Now, you've also got a scale here. 1 centimeter represents 70 meters. So we've got 7.1 centimeters. So we need to do 7.1 multiplied by 70, and that is going to give you an answer of 497 meters. You might have got a different answer if you've done this off the screen, because like I said, we've probably had to shrink the image to get it to fit. And it also depends on the size of the screen you're watching this on. But that is the principle. Whatever distance you got from start to finish, multiply it by that 70, and that gives you the correct distance. Now we've got a diagram of our plane. It shows direction the horizontal forces acting on the aeroplane as it moves in a straight line towards the runway. For question 2.2, we need to determine the magnitude of the resultant horizontal force on the aeroplane. So this is where we need to look at the direction of the arrows and look at the numbers. So we've got a forward motion at thrust of 14,000 newtons. Now we've got friction and air resistance. Now the air resistance and the friction, if you look at the arrows, are both working in the same direction. So that means our resistive forces we need to add together. So you got 4,500 plus 9,500 newtons. That gives you force of 14,000 newtons. So that is our force resisting the motion. That happens to be balanced by the thrust. That's going in the opposite direction, so you would take 14,000 from 14,000 to get the resultant force. Means that we have 0 resultant force. Now we need to describe the motion of the aeroplane as it moves towards the runway. Now this plane is already accelerated, it's already moving. Now if the forces are balanced, there's no resultant force, it means that our plane is going to be moving at constant speed. Well, best answer is constant velocity. Remember, if we've got 0 resultant force, we've got one of two options. Force of the balance, we're either going to have the plane stationary or it's going to be moving at constant velocity. Because the plane is already moving, we know that because we've got the frictional force between the tyres and the runway. It means that we're already moving its constant velocity. And then 2.4, air resistance and friction are contact forces. Give one other example of a contact force. So we've got lots of possibilities. You could talk about tension, you could talk about normal contact force, you could talk about upthrust. Now there's also a bit of a clue. If given you air resistance, they would also allow things like water resistance, which seems very generous. Now they won't accept drag because of course that was mentioned in the previous question in that diagram. But anything like that, you've picked up 1 mark or another mark. Question 2.5. Now we've got the aeroplane stops for a short time and then accelerates along the runway. So figure 5 shows a distance time graph for that stage of the journey. Now we need to turn that into a velocity time graph. Now if we look at the distance time graph, what's happening in this first 10 seconds? Well, the plane is stationary, so it's not moving. So it means in terms of velocity, it's at 0 meters per second. So the first 10 seconds, should be a line drawn right on the x-axis. And then we've got constant acceleration. So we end up, from that 10 seconds, drawing something like that. And that's where we get our 2 marks. So the first mark you get for getting this flat bit, and then the second mark is for our line with a positive gradient. Alright, question 2.6. So the aeroplane takes off from the runway, so its height above the ground increases. Now figure 7 shows the atmospheric pressure, how it varies with the height of the aeroplane above the ground. We need to estimate the atmospheric pressure and the height of the aeroplane above the ground is 10 kilometers. We need to work out the atmospheric pressure. Now, we need to use a graph to do that. Now, we need to work out the atmospheric pressure when we're 10 kilometers above the ground. Now, the only way we can make this useful is by drawing a line of best fit on the graph. Now, try and get that nice and neat. You're going to try and draw a freehand kind of curve, which is going to look a bit like that. Now, if we extend the line upwards until we hit the line, and then if we draw across to the y-axis, I reckon from the way I've drawn that line, we're looking at 29 kilopascals. So I would just fill in 29, and what the examiner would do is they would read your value off the graph. There's a bit of a tolerance there, so if you got anywhere between 26 and 32 kilopascals, you would get the mark for reading off the graph. But your first mark is for drawing your line of best fit, which should be a curve, and extending it out to at least 10 kilometers. Now remember, we've talked about graphs before. Make sure you're not doing using a ruler to do a dot to dot. You'd lose the mark off straight away on that one. If you drew a straight line, you'd also not gain the mark in that particular case. Right, question 2.7. What happens to the air surrounding the aeroplane as the height of the aeroplane above the ground increases? Now, this is where we need to think about I suppose the structure of the atmosphere and what happens as we increase in height. So it starts at the bottom. The volume of air below the aeroplane decreases. Well, that is clearly rubbish, because as we increase in height, the volume of air is going to decrease until obviously we get to edge of space, and we've got very little air there. The temperature of the air increases. Well, no, that's rubbish as well. The higher we go, the colder it gets. The mass of the air above the aeroplane increases. Well, we've got less air above the plane, so how can the mass increase? So that is a load of rubbish. And then the first answer, the average density of the air above the aeroplane decreases. Yep, the higher we go, the less dense that air is going to be, so the air above the aeroplane is going to be less. So we've only got one possible answer in that case. Now that question is worth 10 marks. Well done if you got 10 out of 10. Now question 3. Some cars have a lever that is used to apply the handbrake. So we've got a diagram showing us that. 3.1. The driver applies the force shown in figure 8. The force produces a moment about the pivot. How could the driver increase the moment about the pivot without increasing the size of the force? What we need to do is, you can see where the force is being applied on our handle here. You need to apply the force further away from the pivot. So quite simply, apply force further away from the pivot. You wouldn't be allowed to, it's not an acceptable answer to say extend the length of the lever. That's not really an option in this particular case. Alright, and now the driver releases the handbrake, and we've got a graph now, a velocity time graph showing how the velocity of the car changes during the first 5 seconds of a journey. Now, question 3.2. After 3 seconds, the momentum of the car is 24,000 kilograms meters per second. We've got to calculate the mass of the car. Now, it says use the physics equation sheet. As we mentioned already, you won't have that physics equation sheet, or you certainly won't have this particular formula on there. Now, momentum, mass, and the other factor we've got, if you think about it, is we've also got velocity. So momentum is mass times velocity. Now, after 3 seconds, the momentum of the car is 24,000 kilogram meters per second. So we've got the momentum. Now, after 3 seconds, so if we draw a line up here, we can work out what the velocity of a car was. Draw it across to the y-axis, and the velocity of this car is 15 meters per second. Now, just by saying v equals 15 meters per second, you've got your first mark. This is massively generous. You've got 4 marks for this calculation, and it's being able to use the graph properly. Now substitute the numbers in that we've got. So we've got the momentum, which is 24,000. We don't know the mass, that's what we need to find out, but it's multiplied by 15, multiplied by the velocity. We've now got a second mark for doing that. Make mass the subject of the equation, so we end up dividing 24,000 by 15, and that gives you 1,600 kilograms. And there's your 4th mark. Now, that's just really generous and relatively straightforward to get 4 marks for that one. So remember, we get a mark for using the graph to calculate or work out what the velocity is. We get the 2nd mark for substituting our numbers in correctly, 3rd mark for making mass the subject of that equation, and then obviously the last mark comes from actually calculating the answer correctly. Now in 3.3, we've got to determine the distance travelled by the car during the first 5 seconds of the journey. I've repeated the graph just because we're going to need to use it to work out the distance travelled. Now remember, the distance travelled is the area under the graph. Now, once you remember that, this now just becomes a bit of a maths question. We need to split our graph into geometrical shapes. We've got a triangle and we've got that nice rectangle. We need to calculate the area. So if you remember, area of a triangle is kind of base times height divided by 2. So we've got 15 times 3, but divided by 2. And then we need to add that to the area of the rectangle, which is going to be 15 times 2. And that ends up being 22.5 plus 30. Add those together and you get the total distance travelled, which is 52.5 metres. 3 marks for that, which again, as long as you remember it's the area under the graph, I'd say there's relatively straightforward marks to get. And then on 3.4, in an emergency, the driver needs to apply the brakes suddenly to stop the car quickly. The driver of the car is distracted. Explain why the distraction will increase the stopping distance. Now, this bit is worth 3 marks, so we really need to be making 3 points. So don't forget, stopping distance includes thinking distance. So remember, the stopping distance is your thinking distance plus braking distance. So that's your first point. Now, because the person's distracted, there's additional time while the person applies the brakes. Now, there's additional time while the person applies the brakes. Therefore, thinking distance will increase. And there's your third mark. So, stopping distance, thinking distances, braking distances always come up on paper 2, so it's well worth making sure you're happy with it. Question 3.5. Now explain why the temperature of the brakes increases as they are used. This is almost a paper 1 question really, but they quite often link it into paper 2. So if you remember, work is done by the brakes due to friction. And of course that causes an increase in the internal energy, internal or thermal energy of the brakes. So remember, don't just write friction, that's not acceptable. There's friction in the brakes, that's work being done, energy being transferred, and that causes the brakes to heat up. Therefore, the internal or the thermal store of energy of the brakes is going to increase. That whole question, quite a nice question I'd say, is worth 13 marks. Hopefully you got the full 13 on that one. So question 4, we're looking at a megaphone. It uses a loudspeaker to amplify the sounds that are detected by the microphone. And we've got the diagram there. We need to complete the sentence. So the microphone is used to convert the pressure variations in sound waves into variations in, well, there's different possibilities, variations in current, or you could go for potential difference. And the other possible answer linked to all that is charge flow. Now the first 2 answers are probably the best 2, to try and remember it from that point of view. Question 4.2, the loudspeaker contains a permanent magnet. Which diagram in figure 11 shows the direction of the magnetic fields between the North Pole and the South Poles of the magnet? The magnets are shown in cross section. This one, you just got to remember that our magnetic field always goes from north to south. So if you look at the different diagrams, you can then quickly work out which ones are clearly not correct. That does go north to south, but the bottom bit is obviously incorrect. Here we've got the magnetic field's going from south to north, so that's clearly wrong. And again, this one is clearly wrong because the magnetic field is going south to north, north to south. So it means that the only possible option is that first box where we've got a magnetic field travelling north to south, north to south. Now question 4.3. Some magnets are permanent magnets and some are induced magnets. What is an induced magnet? Well, an induced magnet is, or actually on the side where there's a bit more room, an induced magnet is a material that becomes a magnet when it is placed in a magnetic field. So yeah, think about what induction means, and that will kind of pretty much give you the answer. Now question 4.4, we've got the diagram of the loudspeaker in the megaphone. A current in the coil of the loudspeaker causes the coil to move. So we've got a magnet, you've got a coil of wire, you've got current flowing. What is the name of the effect that causes the coil to move? That is the motor effect, and that's the only possible answer that you can give to that one. Right, we've now got a bit of maths to do, and this is worth 4 marks, so you should be getting a little bit suspicious about this one because there's only one formula to use in this case. Now it says use the physics equation sheet. Unfortunately, the equation that we need to use is not one of the ones given to you. Obviously you aren't going to be getting, or as far as we're aware, you're not going to be having the formula sheet this time around, or the full formula sheet. Now, we should be suspicious. This is worth 4 marks. We've got to calculate magnetic flux density, we've got the length of the wire, we've got a force, and we've got a current. Now, like I said, this is where we're going to be using the formula force equals magnetic flux density, which is represented by a B, it's meant to be a B, multiplied by the current, multiplied by the length of the wire. Now, we're looking at current. We should be suspicious. 4 marks. 16 milliamperes. First thing we need to do is to convert that into amperes. So we divide by 1,000 and you end up with 0.016 amperes. So we've got our first mark now. And from here on, it's relatively straightforward. We're told that the force is 0.013 of a newton. We need to work out B, so that's our unknown, and it's multiplied by our current, which we've converted into 0.016 amperes, and we multiply that by the length of the wire, 6.5. We've picked up another mark. We need to get B by itself, so we need to be dividing by that 0.016 multiplied by 6.5. So you end up with our next mark by making B the subject of that formula. So we end up with this. And then of course just put those numbers carefully into your calculator and you end up with our answer of 0.125, and remember T stands for Tesla. Now you could round that to 0.13, so that would be a perfectly acceptable answer. So just remember, we get a mark for the conversion, second mark for substituting numbers incorrectly, third mark for making the magnetic flux density the subject of the formula, and then the fourth mark for getting the correct answer. Now, if you didn't do the conversion and you just used 16 in your calculation, you'd be out. Your answer would be out by a factor of 1,000. However, you'd only lose 1 mark for that, so they'll only penalise you for the lack of conversion just the once. Right, so next question. We've got megaphones can produce very loud sounds, and a person's hearing can be affected by age and by working in a loud environment. So figure 13 shows how the frequency affects the minimum sound level that can be heard by three different people. So we've got person A, B and C there. We need to be comparing how different factors affect the minimum sound level that these people can hear. And this is worth 4 marks. Now, there's quite a lot in this, so really you need to be looking at the fact that we're comparing two 50-year-olds. One person works in a loud environment, the other one in a quiet environment. You've also got somebody half the age, 25-year-old, who works in that quiet environment. So you can compare the effective age between the two people. So first of all, for all three people, the minimum sound level that can be heard increases as frequency increases. So it means that sounds of a low frequency, they're easier to hear at a lower level. Now in terms of age, what's the effect of age? So we're comparing, in a way, C with B here. Now, you can see from that the minimum sound level that can be heard increases with age. That's quite clear because the graphs are very much separated. And if you look at the differences, so between 2000 and 3000 hertz, the minimum sound level that can be heard increases more in person B, so we've got this bit here, than in person C. The other thing you can talk about is that in person C, there's very little variation in the minimum sound level that can be heard at the different frequencies. It's not a particularly steep curve, or in that case it's a straight line. In B, it's slightly steeper in places, so that shows that the younger person, there's less variation in minimum sound level. Now we're then going to compare A and B. So A is working in the loud environment, person B in the quieter environment. Now the increases in the minimum sound level that can be heard at all frequencies above 2000 hertz compared to working, well, basically increases comparing our quiet environment, which is this lower line, compared with this very steep line initially, and then it continues to increase, but not at such a high rate. Now the minimum sound level that can be heard increases more as frequency increases from 2000 to 4000 hertz compared with the quiet environment. So this is this very steep increase compared with this much more gentle increase in sound. So that's a major difference. Now, I should say. Now, another bit to point out is the fact that these two lines are started in the same place. So working in a loud environment doesn't seem to affect the minimum sound level that can be heard at 2000 kind of hertz. Now there's quite a lot you can go in there, but really this is what this graph is asking you to do. It's getting you to compare the loud environment with the quiet environment. So we can do that because the person's the same age. And then we can compare B with C because that's a 50-year-old in a quiet environment, comparing that with a 25-year-old in a quiet environment. So you need to be making comparisons for both. And if you have a logical answer and you cover most of the points discussed, you're going to get those four marks on that one. Now, question 5. We've got our bumper cars, and of course, give us a diagram just so you know exactly what they're talking about. Now, bumper cars are designed to withstand collisions at low speed. Question 5.1. During a collision between a bumper car and the bumper car and barrier act as a closed system. What is meant by a closed system? Well, there's several different ways we can answer this. Probably the best way to do it is that the total amount of energy of the bumper and the barrier remains constant. So we're not losing, we're not gaining any energy. That's the whole idea of a closed system. You could also talk about the fact that the total momentum of the car and the barrier before the crash equals the total momentum of the car on the barrier after the crash. It's up to you which way you go for that one. Generally I'd go down the energy route, but either way you're still going to get the mark. Question 5.2. How does Newton's third law of motion apply to the collision between the bumper car and the barrier? So remember, this is our equal and opposite forces. So the force of the car on the barrier is equal to the force of the barrier on the car. So our forces are acting in equal and opposite directions. Now question 5.3. During the collision, the change in momentum of the bumper car is 700 kilograms meters per second. The time taken for the collision is 0.28 seconds. Calculate the force on the bumper car during the collision. Now it says use the physics equation sheet, and in this case you get given this formula on the sheet. So it's one of the few that you do actually receive. So when you look at your formula sheet, you will see that force is change in momentum divided by time. We haven't earned any marks yet because that's on the formula sheet anyway. We now need to substitute our numbers in. So we've got time of 0.28 seconds. We've got the change in momentum of 700. So in this case it's only worth 2 marks because we're just substituting numbers in and then multiplying, dividing through. So we've got change in momentum is 700 divided by our time, which is 0.28 seconds. Plug those numbers in your calculator and you get an answer of 2,500 newtons. So remember, first mark, substitute the numbers into the formula. Second mark, calculate the answer correctly. So our bumper car has a flexible bumper. We need to explain how the flexible bumper reduces the risk of injury to the people in the bumper car during the collision. So first of all, having the kind of flex in the bumper, but it can bend a bit, it actually increases the time for the collision to occur. So it increases time for the collision to occur. So that means that our change in momentum, the rate at which that happens is decreased. So the rate of change of momentum is decreased. And that of course results in, therefore, the force on the people inside the car is reduced. Then question 5.5. We've got our bumper car moved with an initial constant velocity and then accelerated at 2 meters per second squared. Whilst accelerating, the bumper car travelled a distance of 1.5 meters and the final velocity of the bumper car was 2.5 meters per second. We need to calculate the initial constant velocity of the car. Use the physics equations sheet. Now in this particular case we do actually, we will have the formula on that sheet. We've got lots of data here. So we've got an acceleration 2 meters per second squared. We've travelled a distance of 1.5 meters and the final velocity of the car was 2.5 meters per second. Now when you look at the formula sheet, you'll find this formula. So the final velocity squared minus the initial velocity squared equals 2 times the acceleration multiplied by the distance travelled. If we now substitute our numbers into that formula, you end up with, well, we've got our final velocity of 2.5 squared minus u squared equals 2 times our acceleration, which is 2, multiplied by the distance of 1.5 meters. We now need just to start multiplying through these numbers. So 2.5 squared gives you 6.25 minus u squared equals 2 times 2 is 4, multiplied by 1.5 gives you 6. We now need to get u squared by itself. Let's make it positive, so we'll swap to the other side. We've got u squared equals 6.25 minus 6. That means that u squared equals 0.25. We then need to square root that, so we end up with u equals 0.50. And there's our answer, 0.5 meters per second. 3 marks, nice straightforward. Obviously you don't get the mark for the formula. First mark, substitute the numbers in correctly, and then second mark is for essentially getting u squared by itself, and then of course the third mark is calculating the answer correctly. That question worth 10 marks. Hopefully you got 10 out of 10 on that one. Okay. Question 6, a little bit about space. So we've got the Hubble Space Telescope orbiting the Earth. What name is given to objects that orbit a planet? So satellites. So we have artificial and natural satellites. So in this case, the Hubble telescope will be our artificial satellite. And then question 6.2, we've got a space telescope that uses microwaves to communicate with the Earth. A microwave has a wavelength of 12.5 centimeters, and we've got the speed of microwaves through space. We should know that it's 3 times 10 to the 8. That's the same speed of light. Calculate the frequency of the microwave. Use the physics equation sheet. Well, unfortunately, we don't get that one, and we've got to give our answer in standard form. Now, this question is just so generous, the fact that we're getting 5 marks for it. Now, if you think about it, we've got to calculate frequency, we've got the speed of the waves, we've got a wavelength. So we're going to be using our wave equation. Wave speed equals frequency multiplied by wavelength. However, that's the only formula that we need to use, so we've got to be suspicious again. And the bit you need to be suspicious on is our wavelength. You need to be converting 12.5 centimeters equals 0.125 of a meter. Now, just by doing that conversion, you've picked up your first mark. Once you've done your conversion, substitute our numbers into the formula. So we've got 3 times 10 to the power of 8, it's our wave speed. Frequency, we don't know, multiplied by 0.125. We've now got a second mark. Make frequency the subject of the equation, and we end up with 3 times 10 to the power of 8 divided by 0.125. That's going to give us a very big number, and as a regular number that comes out as 2,400 million. Be careful with the zeros, and that's in hertz. Now, of course, we need to turn that into standard form, so it's going to be 2.4 times 10 to the, so look, 1, 2, 3, 4, 5, 6, 7, 8 to the power of 9. 5 marks for that. That is just super generous. So just as a reminder, 1 mark for the conversion, 2nd mark for substituting the numbers in, 3rd mark for making frequency subject to that formula, 4th mark for getting your number, 5th mark for converting into standard form. That just seems very, very generous. Alright, 6.3. Explain the effect of the Earth's gravitational force on the motion of the Hubble Space Telescope. So the gravitational force causes Hubble to accelerate towards the Earth, and that changes the direction of the motion. but not speed. Therefore, this changes the velocity of the Hubble Space Telescope. So remember, you can still be moving at the same speed, but if you change in direction, that means that you're constantly accelerating, and that's how things like our satellites stay in orbit. Right, 6.4. We've got the Hubble Space Telescope can detect visible light from distant galaxies, and the visible light spectra from stars and galaxies include dark lines at specific wavelengths. So below we've got an example of this, and it's from the Sun and two galaxies. So explain what conclusions can be made about galaxies A and B, and this is worth 3 marks. Now straight off, we are looking at redshift. We're increasing the wavelength, so our waves are getting longer. They're shifting more towards the red side of the spectrum. Now, galaxy A has greater redshift. So that's our, I suppose, the more obvious conclusion. Has greater redshift than B, which means that galaxy A is travelling away from us faster than galaxy B. And then that also means because galaxy A is further away from us, than galaxy B. Remember, the more redshift that you have, it means that that particular galaxy is going to be further away and travelling faster. So there's our 3 marks on that one. Redshift frequently comes up, so make sure you're happy with that. That's worth 12 marks. Hopefully you got 12 out of 12 on that one. Question 7. So we're going to investigate the behaviour of light, and the student used a mirror with a smooth surface to investigate reflection, and you can see the equipment being used. 7.1. What name is given to a reflection from a smooth surface? You just need to remember that term, specular, and that's the only acceptable answer on that one. Now, the student measured the angle of reflection for different angles of incidence. What conclusion can be made from the results in table 2? Well, the results should be angle of incidence equals the angle of reflection. And that's it. Nice, easy mark. Now, question 7.3. What type of error caused the variation in the results of the angle of reflection? So we've got slight variations in it. This type of error is one of those things. It's a random error. Now, what might cause that error? Well, it could have been that the student's kind of head might not have been in the same position each time. Also, probably the better answer, or one of the best answers, the center of the ray of light may not have been marked correctly. So remember, if you've done this before, you get slight variations in your answer. Also, you could also get away with saying that the protractor may not be in the correct position. So that's another possible answer. So remember, 1 mark for the type of error, which is random, 2nd mark for an explanation. Now, the student also investigated the refraction of light. So that's where light bends, will turn as it hits another medium. Now, figure 18 shows the path of a ray of light through a glass block. So why is refraction not occurred? Well, in this case, all the points on the wavefront enter the glass at the same time. On the wavefront, enter at the same time, which means that the ray of light, all of the wavefront is going to slow down at the same time. Therefore, you're not going to get any turning in the ray of light. Now, 7.5, the student measured the angle of refraction for different angles of incidence, and we've got the protractor used. We're showing the different measurements. Explain why the student should not have recorded these results when using the protractor to make the measurements. Now, the clue here is we've got 6.0, 6.3, 6.4, 5.8. Well, if you look at the protractor, there are no decimal places on our protractor, so it's all about the resolution. So remember, the resolution of the protractor is 1 degree. So theoretically, we can't actually make any measurements smaller than that with any real kind of accuracy. Therefore, could not be used to measure the difference between results. So remember, with a protractor like this, we could only measure these angles to the nearest whole degree, and that's where you're going to get your second mark from. So things like resolution will come up, could be on any of the papers. Obviously, it's come up on this one today. Now, 7.6, we've actually got some refraction happening, and figure 20 shows what happens to wavefronts as they pass across the boundary between air and glass. So now this time we get refraction because the wavefronts are entering the glass at different times, and the velocity or the speed of light is less through glass, which means that in a way the right hand side of the wave slows down first, because that's entering the glass first, but the left hand side keeps on moving, and that causes that turn at the junction here. But then of course, once all the wavefronts are in the glass block, they continue to travel in a straight line. So where do we get 3 marks from? So different parts of the wavefront enter the glass at different times. So this refraction can only happen when the light hits at an angle, basically. The velocity or speed of light is less in glass. Therefore, one part of the wavefront changes speed before the other parts. And there is your 3 marks. Now that whole question is out of 10, quite a nice question. So hopefully you got 10 out of 10 on that one. Okay, question 8. So we've got figure 21 shows a transformer used to power a lamp using the mains electricity supply. Alright, so what material is used to make the core of the transformer? Give the reason for using this material. We always use an iron core because it is easily magnetized. Or you can talk about it being a magnetic material. That would be acceptable. Now the other materials you could use would be nickel or cobalt, but obviously iron is used much more commonly because it's a lot cheaper and a lot easier to get hold of. Question 8.2 now, 5-mark question. It's another maths question, and it's a nice one. You need to get used to or get kind of comfortable with your transformer questions. So we need to determine the current in the secondary coil when the power output of the transformer is 6.9 watts. We're assuming that the transformer is 100% efficient, and in this case we can use the physics equation sheet. So there's two different ways we can answer this question. Now, I've shown the transformer setup with a number of coils on the primary and the secondary part of our transformer. We've also got the 230 volts from our mains electricity. Now the formula we're going to use in this particular case is the potential difference in the primary coil divided by the potential difference in the secondary coil equals the number of turns on the primary coil divided by the number of turns on the secondary coil. Now we can add in some of those numbers. So we've got our primary potential difference, that's 230. Now that 230 divided by our potential difference, we don't actually know that one, equals number of turns in the primary coil, which is 2000, divided by 40. That means that our VS, I just need to do a little bit of manipulation there, equals 40 divided by 2000 multiplied by our 230. Now that is going to give us a potential difference of 4.6 volts. That's not the final answer because that's giving us a potential difference. We need to work out the current. We've also got power though. So substitute the numbers into our power equation. P equals IV, or P equals VI, depends how you remember it. So our power, 6.9 watts. Current is a known multiplied by 4.6 volts. If we get I by itself, it means that we've got 6.9 divided by 4.6. The numbers are quite nice to us. That gives us a current of 1.5 amperes. So that would give us the full 5 marks. Now there's an alternative way to do this, and this is where we're using the other physics formula where it's IS multiplied by VS equals IP multiplied by VP. Now you might be thinking, well, we haven't got the current or the potential difference in our secondary kind of setup. However, we've got the power output, which is 6.9 watts. Remember, P equals IV. So this part of the equation is basically the power output. So you can substitute in that 6.9, and that equals the current in the primary, which we don't know, multiplied by 230. We then shift things around a little bit. IP equals 6.9 multiplied by 230. That gives us a current in that primary coil of 0.03 amperes. Now this is where we need to again use the previous formula, and we end up therefore with the current in the secondary secondary coil ends up being that multiplied by, this is where a number of coils comes into effect, and that ends up giving us 1.5 amperes as well. Whichever method you choose and you get the correct answer, you get 5 marks. Personally, this is probably the way I would have gone with it, but at the end of the day, it really doesn't matter which way you do it, as long as you get the right answer. That's worth 5 marks, which takes a bit of manipulation, but I suppose you're using 2 formulas in that case, so that's really why they're being quite generous with those 5 marks. But well done if you got the 5 marks on that one. That total question's worth 7. Okay, last question, and this one probably one of the tricky ones because the dynamo often gets forgotten about. So the dynamo is used to generate an electric current. So here we've got our diagram. It shows the inside parts of the dynamo connected to a lamp. So this one, 5 marks. Explain why a direct current is induced in the coil. Now, the coil moves through the magnetic field. So our coil wire moves through the magnetic field. Remember, movement of a coil of wire through a magnet is going to induce a current. So it means a potential difference is induced in the wire. So as there is a complete circuit, there is a complete circuit, so a current is induced. That's in the coil. Now, because each half turn, the 2 ends of the coil swap from one brush to the other. So it means that the direction of the induced current doesn't reverse every half rotation. So remember, because each half turn or half revolution, half turn, the 2 ends of the coil swap from one brush to another. So the direction of the induced current, the potential difference, does not reverse. Okay, so that's worth 5 marks. So it's worth having a look at that kind of answer. Quite often you get questions about the motor effect, you know, how an AC current might be, or the generator effect I should say, how an AC current is developed. In this case it's a dynamo, which is just direct charge. Now what does our graph look like? So sketch the graph, and we need to complete 2 revolutions. So we're looking for something like this. And there's our 2 complete revolutions. Now, you could just change colour. The other possible answer is, depending on how you wired up your dynamo, that could be the other acceptable answer. But you just got to make sure that you're either having completely positive potential differences or completely negative. Either way, you still, in fact, you only get 1 mark, which is a bit miserable on that one. Now the final question: a lamp is disconnected from the dynamo. explain why the dynamo becomes much easier to turn. So if you remember, after we've disconnected the dynamo, there is no longer an induced current. So there's no magnetic field produced. No magnetic field produced by the coil to oppose the movement of the coil. So that's worth 3 marks. Quite a nice kind of 3 marks. Again, it's one of those questions that does come up quite frequently. Make sure you're happy with the explanation there. Now that's questions are worth a total of 9 marks. It also brings us to the end of the paper, so that whole paper is worth 100 marks. So well done if you got 100 out of 100. Well done.